Hi everyone. So welcome to this video. In this video, we will be discussing an example of pipe flow and electric circuit analogy. And if you haven't had the time to go through the previous video, please do that because there is where we discussed how we can actually relate pipe flow to electric circuit, and you will actually be using formulas that we derived in last video. So if you haven't had the time, please go and watch that video because we will be sort of using it quite frequently in this video. So let me explain the problem that has been given to us. We have been given that there are two pipes which are connected to each other as shown here. So there is pipe 1 with length L1 equal to 1 meter, and then pipe 2 with length also equal to 1 meter. We have given that the first pipe has diameter 1 millimeter and the second pipe's diameter is unknown. And water is flowing through both the pipes, so the flow rate has not been given to us. But we know that the viscosity of water is 10 to the power minus 3 pascal second, and density is 10 to the power 3 kg per meter cube. We've also been given that the pressure drop from the inlet of the first pipe from here, this point, to the outlet of the second pipe, this point, or total pressure drop is 10 to the power 3 pascals. And we have been asked to find D2 given that the fluid or the water spends 3 minutes in the first pipe. Okay, so this is something new. We haven't seen something like this before, so we'll see how we can use this. But the basic structure, the basic newness of this problem is that you have two pipes now connected to each other. And when you have pipes which are connected to each other in the way shown in the figure, the first thing you can see is that fluid is going to be same in both pipes. You can imagine that is true because mass balance has to be satisfied, right? Because mass balance has to be satisfied, flow rate is same in both the pipes. Now, whenever flow rate is same in both the pipes, and whenever you have systems, two pipes or three pipes, whenever flow rate is same, we can write them as a series system. And this is again something we have discussed in the previous video. We can write that there is a pressure inlet where pressure is analogous to potential or voltage, and an outlet pressure, and current is analogous to flow rate. And then pipes can be written in terms of resistances, where resistance 1 is 128 mu L1 by pi D1 raised to the power of 4, and R2 is resistance 2 is 128 mu L2 by pi D2 raised to the power of 4. And the net resistance R effective is R1 plus R2. Right? This has been again something we have discussed in last class, and what we discussed was that Q can be written as P in minus P out by R effective. However, before I start jumping into applying this formula or sort of calculating anything, I should remember that this is only valid, the whole circuit analogy is only valid if flow is laminar in both pipes. Laminar in both pipes. Right? So the way we check that the flow is laminar in both pipes is by checking the Reynolds number. That Reynolds number 1 and Reynolds number 2 both have to be less than 2100. So this is something we have to check either before solving the problem if we have enough information, or we have to assume that the flow is laminar and then cross check later on once we have all the information. Okay. So now we have been given, we know that let us see what we have. We have the length of the pipe, we have the diameter of the pipes, but that does not tell us anything about the flow rate or the velocity, which is important to calculate Reynolds number or flow rate. So even if we have to check with this condition of laminar flow, or we have to apply this formula, we need flow rate. Now, what we haven't used till now is this time which has been given to us, the time the water spends in the first pipe. So it is very straightforward to actually think about this, that T1 can be written as L1 by U1. Since velocity in the first pipe will be constant as a function of length or as a function of position in the pipe, uh, and because the flow is fully developed, that is something we have discussed in class, we can just write T1 as L1 by U1, or we can find U1 as L1 by T1, and the length is, since length is 1 meter and time is 180 seconds, you can actually calculate this to be 5.5 into 10 to the power minus 3 meter per second. Again, you can run the numbers and cross check this. So this is 5 into 5.5 into 10 to the power minus 3 meters per second, or 5.5 millimeters per second. Okay. Now that since we know the velocity, we can calculate the flow rate. We should note that flow rate is same in both the pipes. So we can write that pi d1 square by 4, pi d1 square by 4, which is the cross sectional area of the first pipe, into velocity in the first pipe, is equal to pi d2 square by 4 into u2. I hope this makes sense because the flow rate is same in both the pipes. We can write this. Now here we know d1, we know u1, but we don't know d2 or u2. So we cannot really calculate something for the second pipe, but we can at least calculate the flow rate based on the information from the first pipe. So if we write q as pi by 4 into d1, which is 1 millimeter square, into u1, which is 5.5 into 10 to the power minus 3 meters per second, this will actually come out to be 4.4 into 10 to the power minus 9, 4.4 into 10 to the power minus 9 meter cube per second. Okay, so this is something we know. So we now know the flow rate based on using the time which we had discussed. Okay, so now we have flow rate. So we know the flow rate in both the pipes is same, and we have the flow rate, but we do not know the velocity in the second pipe because we do not know the diameter of the second pipe, and that is something we have to find out. So to check the condition of laminar flow in both the pipes, we should know the velocity in the second pipe also, but we cannot do that right now because we don't know. So let us first assume this. So let us assume that the flow is laminar. Okay, so assume flow is laminar. And use Q's P in minus P out by R effective. Okay, so we know Q is 4.4 into 10 to the power minus 9 meter cube per second. We know P in minus P out, or the total pressure drop, is 10 to the power 3 pascals, and we know R effective is R1 plus R2, right? R effective is R1 plus R2, where R1 is 128 mu L1 by pi d1 raised to the power 4 plus 128 mu L2 by pi d2 raised to the power 4, or we can write this as 128. We can take out, put the values, and since L1 and L2 are 1 meters, we can just put them directly, and 1 by d1 raised to the power 4 and 1 by d2 raised to the power 4. And again, d1 is also something we already know. So you'll have to put this back. You will have to basically write this whole equation, that this will become, let me just write it down for you so that you can cross check directly, that 1 by d1 raised to the power 4 plus 1 by d2 raised to the power 4 basically becomes 10 to the power 3 by 4.4, sorry, 4.4 into 10 to the power minus 9, basically the flow rate. So I'm taking flow rate to the other side, basically dividing, taking flow rate here and taking R effective, some part of R effective here, and then this will become pi into pi by 128 into 10 to the power minus 3. Okay, so you can check whether this is correct or not, and then um, we can put the value of d1 as 10 to the power of minus 3 meters, and then you can find the value of d2 actually directly. So I will not be going further in details, but just giving you the answer. This will come out to be 0.679 millimeters. Okay, so we have d2 now. So d1 was 1 millimeter and d2 is 0.679 millimeters. Okay, so I hope you were able to follow what we did, but we are not done yet. We were asked to find d2, but now we have to cross check that whether Reynolds number 1 and both Reynolds number 2 are less than 2100, right? Because that was our assumption. So we can write that RE1 is rho U1 D1 by mu, and RE2 is rho U2 D2 by mu. Now we know rho, we know U1, we know D1, and we know mu, but we do not know, we know our rho, we know D2 now, we know mu, but we do not know U2. But we can find U2 by using the formula that we had discussed here, that we know the flow rate, because flow rate is same in both the pipes. So we can find U2 by using this relation, because now we know D2. So you can find U2 by using the relation Q is pi D2 square by 4 into U2, right? So I'm not actually showing you the calculation here. You can again cross check that. Both of them come out to be, both are satisfied, both conditions are satisfied, and they are actually way less than 2100, so they're very definitely laminar, and you can cross check again to see these numbers. But the idea here was to really show you that we can, rather than solving the system in a more complicated way, we can just write down one equation that Q is P in minus P out by R effective, where R effective is the sum of the two resistances, and just solve the problem. So I have not gone through a lot of number crunching here. Like, you can basically find out numbers yourself and verify, but I hope you are getting the idea that if the flow rate is same, we can write that down in the series circuit, and just add up the resistances, and if you know the total pressure drop, it will be very easy to find out whatever variable we have to. One new part here was that we were given the time in the first pipe, and that we just used to calculate velocity, and then we could calculate flow rate. And at the last, we just had to check, once we had the diameter of the second pipe, that whether the Reynolds number satisfy the laminar system or not. So you can see that using circuit analogy, we can actually solve problems which have two pipes as opposed to one pipe. And I hope that you found this video useful and interesting, and hope to see you in the next video.